This is the pre-lab lecture for Activity 12, and that's for Monday, April 20th. So if you take a look here, our announcements, couple things. You've got things to do, okay? First, I really encourage you wrap up Experiment 4. Finish the post-lab for that. I know it's not due till April 27th, but I would encourage you wrap up that experiment before you start on Experiment 5. Experiment 5 will be on Wednesday, April 22nd, but go ahead, wrap up Experiment 4. You also can see there's an exam coming up, so that's the following week, Monday, April 27th. That covers activities 7 to 12 and experiments 3 to 5. If you're considering withdrawing, let me know. I can give you some more information. That deadline is May 8th. I really encourage you, see me during office hours, Monday, Wednesday, 12:30. Your classmates come and they get feedback on their activities. We go over labs. It's a really good thing to do, so come see us there. There's still room for all of you to come join us. Activity 12, Experiment 5, that's what's coming up this week. So for today, we're going to look at things you may be familiar with. We haven't covered them in lecture yet, but they're coming up. That's molarity, mass percent, and molality. These are all different ways to talk about concentration. So we'll talk some about that. And then we're going to see how we can use concentration as a conversion factor. You've already done some work with dilution in the lab, so now we'll do the theory behind it. What are the units, how to do those calculations, and so on. That's dilution. And that'll get us to stoichiometry. So these are converting grams, moles, particles, concentration from one substance to that of something else. STP, you may recall from Chem 152, this is referring to gases. So that gets worked into this activity as well. And then there's a lot of pages of calculations, so you definitely want to take into account sig figs. So I'll be giving feedback on proper sig figs. So as usual now, the activities will be on Lab Archives. You submit your work. I really encourage you, be comfortable with converting all your pictures to one PDF, upload one PDF as an attachment, and now that looks like a presentation. Some of your photos have been rotated wrong. It's been poor quality. So make sure you know how to submit one PDF. You will have to do that for quizzes and exams. Submit one PDF. So make sure you can do that. So the activity is the plan for today, but there's other things you can do. If we were doing this on campus, I would let you know that this activity does not take the whole time. Stay and work on Experiment 4 post-lab or Experiment 5 pre-lab. All right, so concentration. This is, broadly speaking, is it concentrated or is it dilute? Those are conceptual. Is there a lot of stuff in it or is there not much at all? So we got ways that we can describe that. Molarity is moles of solute, and that's liters of solution. So I know this looks the same, solute, solution, so I'll write out solution. And what's in a solution? That's the solute and the solvent. Okay, so we want to make sure we have those terms separate. The solvent is in larger amounts versus the solute smaller amounts. So moles of solute, liters of solution is molarity, and that equals capital M. So anytime you see molarity, you've used 6 molar hydrochloric acid, 3 molar or 1 molar sodium chloride, rewrite it right away to 1 mole of sodium chloride, 1 liter of solution. That's how you want to use this. Mass percent, if it's mass, it's in grams. So that's grams of the solute over grams of solution. And this is a percent, so that's our 100 that we factor in. That's times 100. So that's mass percent. Molality gets introduced in this activity. You really won't use it significantly until Chem201, but it's a really important concentration term. And if you look, it's moles of solute. Okay, that looks familiar. But the bottom is different here. This is kilograms of solvent. Okay, so if you look, this is a mass over mass calculation, and the reason this is so important is it is temperature independent. Okay, what I mean by that is if you have a 1 molar solution, that concentration, the molarity actually changes at 0 degrees Celsius or 85 degrees Celsius. However, if you have a 1 molal, molality is lowercase, italicized m, it is temperature independent. So it's the same molality at 0 degrees Celsius as it would be at 85 degrees Celsius. So no matter what you have, whether it's molarity, mass percent molality, you can use it in this equation. So maybe, now I'm changing it up a bit, C1 times V1 equals C2 times V2. This is the dilution equation, and I'm just putting in it in any general concentration term. Maybe you're more familiar with it in molarity, so that's M1 V1 equals M2 V2. But you could put it in mass percent. You could put it in molality. Your volume also doesn't have to be in specific units. That could be in milliliters, or it could be in liters. They just have to be in the same units. So this concentration, if it's in molarity, then the volume has to be in the same units. Over here, if we put this one in mass percent, then this one needs to be in mass percent. So that's how we use our dilution equation now with all of these different concentration terms. So this may look familiar. This is the roadmap. So grams, moles, particles of one thing. So that's grams of X, moles of X, particles of X. So that means to go from grams to moles, that's our molar mass. Moles to particles, that's Avogadro's. And if we're in moles of X to moles of Y in stoichiometry, if we're going to something else, that means we have to use a balanced chemical equation and use the mole ratio. So how many does react with the other substance? So that's the mole ratio here. And again, this is still molar mass, Avogadro. So most of this framework, I think, should be familiar to you. What we're adding today, so really emphasizing mole ratio comes from balanced chemical equation. But what we just did on the slide before, there's other ways to get to moles, okay? We can go from molarity. We can go from molality. Remember, these are conversion factors now. So if your molarity, which we rewrite as moles per liter, and you're given liters of something, you just take that and multiply it, and you get moles, okay? Well, that gets us back into this framework. If you have moles, then you can convert it to grams. If you have moles, you can convert to particles, or you can convert to moles of something else. So liters times molarity gets you to moles. Well, you can also go to volume from that. So what if you had moles? So moles of X or moles of something else. Now you divide by molarity. That is a conversion factor to get to liters. So these equalities that we're setting up, molality, molarity, whatever it is, they can be used in two different ways as conversion factors. So that's the main thing wanting you to see here. And lastly, you can see it kind of gets thrown in this calculation section, but I really want to emphasize a few things. This STP stands for standard temperature and pressure, but that is only for gases. Okay, so make sure you don't look at this and say, oh, wait a minute, I've got mole to liter. Well, that sounds like concentration. No, this is only for gases. And at standard temperature and pressure, 1 mole of any gas equals 22.4 liters. Okay, that's what the molar volume, 22.4 liters, is at STP. So standard temperature, that's 0 degrees Celsius, or 273 K. And standard temperature, you did this in the gas laws, probably in Chem 152. Pressure is 1 atmosphere, or that's 760 millimeters of mercury. So again, I want to caution you, this one happens all the time. Well, I need to convert moles to liters or liters to mole, and then, wait a minute, I know, 22.4 liters. That has to be for a gas, and the gas has to be at STP. So like I said, this activity will have a lot of calculations, a lot of times to practice, concentrations, stoichiometry. So come see me during office hour if you want to go over this activity.